Imaginary numbers. Now we all know what real cows look like. Of course, these are just photos of real cows. And if you've been through my class, you probably know that I often put up imaginary cows. Same situation with numbers. We have real numbers. We have imaginary numbers. Now, the first set of numbers we ever worked with were natural numbers, right? Starts with 1, and 2, then 3, goes on forever. Capital N to describe that set. And then we moved on to whole numbers. 0, 1, 2, 3, etc. We use a capital W for those. Integers, well, we take the whole numbers, but we can either leave them positive, or 0, or negative. Notice this list goes on forever in both directions, right? It's not limited to just the positives. Quite often we'll use Z for integer, because if we say the word integers, it kind of has a Z sound at the end. When I was a youngster, we would use the letter J. My understanding is that comes from a German word for integer, although I can neither confirm nor deny that. Rational numbers. Any number that can be written as a ratio. So this is your natural numbers, your whole numbers, your integers. Fractions, whether they're positive or negative. Decimals that terminate, and decimals that go into a repeating pattern. We use Q, although when I was a youngster, we actually used capital R for rational. Now, rational comes from the word ratio. Any rational number can be written as a ratio. So if I see the number -4, I'm thinking, oh no, it's -4/1. If I see a 7, I go, no, it's really a ratio, 7/1. Notice these are also fractions, right? A ratio is a fraction. 0.25, I can rewrite that as 1/4. 8.3, 83/10. A weird decimal that repeats forever? Hey, 0.3 repeating, that's 1/3. An even more bizarre repeating pattern, right? 0.363636 repeating, that's 4/11. Any decimal that terminates, I can change into a fraction. Any decimal that goes to a repeat pattern. And so that's why we use Q, right? If we look at a ratio, also known as a fraction, there's division happening, right? It's a quotient. 4 divided by 11, right? That is a quotient. That's where the Q comes from. And then we have our good friend, the irrational numbers. The only numbers that qualify as irrational are the really odd decimals that do not terminate and do not go into a repeat pattern. I'd like to use capital I for irrational, but if you pick up 5 different math books, you might find 5 different ways they use that, right? The NWZQ is pretty consistent from math book to math book. Irrational, you'll kind of find some oddball things. And then for the real numbers, if we take all the rational numbers and combine them with all of the irrational numbers, those are the real numbers. Now, of course, when I was a youngster and we used capital R for rational, we would then use a script capital R for real. Now, to avoid confusion as time has gone by, more and more mathematicians have decided to use Q for rational instead of R. But if you look up any math textbook and start reading away, or even on the internet, you'll quite often see that the real numbers, they still use that script R. In fact, sometimes they'll even just start the word real with using the script R and then go back to regular text for the rest of the word. Side note, numbers like Pi and E are transcendental numbers, a subset of the irrationals. We'll talk more about that at some other point in time. So here is the family of real numbers. Thank goodness I've got some spare side on the right-hand side of the screen. All right, natural numbers are a subset of whole numbers, which are a subset of integers, which are a subset of the rational numbers. Transcendental numbers are a subset of the irrational numbers. And then if I combine the rational numbers with the irrational numbers, we have real numbers. Okay, now I gotta slow down a little bit. What kind of numbers are not real? Well, we've got a major issue in math. All right, square root of 9, no problem there. That's just 3. Negative symbol out in front, no problem. That's like -1 times square root of 9, which is -1 times 3, or -3. Here comes the issue. Look where that negative symbol is. That negative symbol is inside the square root. That is the issue. That's the problem. We usually just write no solution. Well, that's not quite true. If we're limited to real numbers, then it definitely is no solution. So we need some imaginary numbers so we can work with this situation. The number I is an imaginary number. The definition, I squared equals -1. Okay, that's how that number is defined. This is kind of weird. We don't really tell you what I is, but we tell you that if you take I and you square it, you get -1. Now, that enables me to find the square root of -1. Right? If I want to find the square root of -1, I say, oh, that's going to be my imaginary number, I. Kind of a backward definition if you think about it. I would have thought you'd define it as I equals square root of -1, but instead mathematicians have defined it as I squared equals -1. All right, go figure and have a debate with some mathematicians about that one. So let's go back and let's look at square root of -9. All right, I can actually find a solution. I know that -9 is really 9 times -1. Notice I put the number 9 first and I put the -1 second. This is just the customary way of doing this. Of course, that means I can do the square root of 9 times the square root of -1. Square root of 9, of course, is just 3. And square root of -1 is I. We have an answer now. The square root of -9 is 3i. Now, how would I check my answer? Well, let's square it. Let's take 3i and let's square it. In other words, 3i times 3i. Multiplication is wonderful because we can use the associative property, or in this case, we can use the commutative property, right? I can change the order around because it's all multiplication. 3 times 3 will become 9, right? Because that's 3 squared. I times I becomes I squared. And so the 3 times 3 becomes 9. The I times I, also known as I squared, becomes -1. And sure enough, if I multiply, I get -9. So if I start with the square root of -9, the answer is 3i. If I start out with the 3i and I square it, I get -9. Let's try some examples here real quick, some square roots. Square root of -9. Well, you better get this one right. We just did it. right? 3i. Square root of negative 25, 5i. Square root of negative 64, 8i. Negative square root of 81. Don't fall asleep. The negative was outside. You just get negative and then a plain old 9. Square root of negative 4, 2i. Square root of 9/25. Okay, now remember with a fraction, I can take the square root of the numerator. We'll get 3. Take the square root of the denominator. I'll get 5. There's the answer, right? 3 times 3 is 9. 5 times 5 is 25. Now, what if I stick a negative inside there? Well, 7 times 7 is 49. 10 times 10 is 100. And then I got an I. Now, sometimes students are kind of looking like, well, gee, how come there's just one I when there's two different numbers in there? Okay, if I think about this, it's like I got the fraction of 49 over 100 times negative 1. And so when I do square root of 49 over 100, that's just going to get me 7 over 10. And then, of course, square root of negative 1 gives me an I. Right? So if you're looking and say, wait a minute here, there's more pieces now. It's like, no, it's still just a number times negative 1. So it's still just the square root of the number times I. So we've got a new neighbor in town. The imaginary numbers are moving in. Notice they are not real numbers, right? They're off to the side. But this diagram is not done. It's done for today's presentation. But we will add something to this in the future. That's right. You get to play with an imaginary friend today. You can tell your parents, I'm playing with an imaginary friend. In fact, my teacher insists that I play with an imaginary friend. You can play with your imaginary friend, I. I'm always kind of leery of things I find on the internet, but supposedly this is an actual photograph. Kind of a rare occasion, but sometimes you get the rainbow effect, the way the sunlight will actually hit a wispy cloud. And so this is purported to be an actual photograph. And if that is a real photograph that's not been photoshopped, that must have been a spectacular sight to see in person.